Welcome back. We are going to start from where we left, the fully differential operation and the DC biasing and stability analysis for the fully differential operation. So here, summarizing what we started with, we looked at the common mode feedback and we did the stability analysis for that, and our assumption is that the common mode feedback loop is having very low bandwidth. It is not propagating any significant signal content. As a result, we are assuming that the voltage provided over here by the common mode error amplifier is almost constant. It is just a DC bias, and therefore we are putting an AC ground over here in the AC equivalent circuit. Even if there is a significant common mode at the input, the differential amplifier also ensures that the common mode at the output is sufficiently small. So the common mode signal anyway will be small, but apart from that, the bandwidth of the error amplifier can be made to be potentially very small so that it does not propagate any significant component of the common mode signal. As a result, you will just have a DC bias point. So that is the reason why we have put an AC ground over here, assuming that this is relatively constant DC potential provided by the common mode feedback circuit. And we have the differential signal Vd minus Vd at the input, and we just wrote down the expression for the overall gain for this particular amplifier from the differential input to the differential output, VO plus minus VO minus upon Vi plus minus Vi minus. So that is having GMRO by 2 whole square. And we need to look at two things. What is the first is the analysis of the closed loop stability. For that, we need to look at the feedback operation and the stability analysis for this feedback operation. And second thing, we also need to check the DC bias, just like we did for the common mode feedback. So let us start with the DC bias and look at how to establish an appropriate DC bias point at the input nodes of this fully differential amplifier. So remember that using the common mode feedback, we are assuming that we have already set the output DC bias to an appropriate value, and also the DC bias at the output of the first stage has been set to an appropriate value, a desired value. Now the next question is, how do we set the input DC bias? So if we recall some of the very common steps that you might have taken in an undergrad lab to bias differential amplifier or a common source amplifier, it is using a voltage divider. So for a differential amplifier, possibly we can think of using a voltage divider. You can connect an voltage divider to get an appropriate DC bias point that you want over here, and then you can use the capacitive feedback as we have discussed in the beginning. But once again, what is the problem with such bias? The biggest problem will be the noise contributed by these resistors, because ultimately these resistors are going to give you an input referred noise, which is going to come directly at the input port, and it is going to interfere with your amplifier's operation, and therefore direct resistive biasing may not be a good option. Likewise, it will also degrade the input impedance. So here putting the resistive dividers will degrade the input impedance. Rather than the signal coming at the gate through the capacitors, you are now having a low pass filter formed with the help of this resistor. So it is going to affect your frequency response, input impedance and noise, and therefore using these resistive dividers may not be a very good option. Apart from that, this will also waste some of the static power, because if you are having a voltage divider, unless you are having very large resistances of mega ohms range, it may burn few microamperes of power, and that can also lead to wastage. So rather than using voltage dividers at the input port, we are going to take help of already established DC bias point at the output to bias my input nodes, and for that we are going to use resistors in parallel with our feedback element. Let us see how does this help, and how does this not violate our other constraints. So we have to choose appropriate values of this R and make sure that it is helping us in establishing the appropriate DC bias point at the input terminal of our differential amplifier without violating the frequency response or the noise constraint of our overall amplifier. So in the very beginning, we have said that we don't want to use resistive feedback. We don't want to use R1, R2, and one of the main reason is that it can lead to a lot of noise, because R1, whatever noise is being contributed by R1, that will get amplified by the amplifier, and it can increase the input, the overall output noise of the amplifier, and also the equivalent input referred noise, as a result will be bad. So, that was the starting point why we chose the capacitive feedback. Now, in this case we are saying that we are again going to take help of these resistors in the feedback network to establish an appropriate DC bias point at the input. So, let us see how does that help us in first of all establishing DC bias without violating noise constraint, and then look at the frequency response criteria. So, for the analysis I will look at the single ended version, because that is simpler to analyze and visualize as well. So, I will stick to the single ended version, where I am having the C1 C2 for the feedback realization, and I am having a feedback resistor RF for the DC bias. You are having the input signal applied here V in, you can call it C1, you can call it C2. So, I am just going to use the single ended version for the analysis, and results remain valid for the differential case also. Now, if we look at the overall operation of this inverting amplifier and consider the role of RF, we can visualize the role of RF by say constructing a feedback network based on resistors. So, let us see if I have the resistive elements in the feedback, what are the roles or what are the contribution of these two resistors R2 and R1 in the overall noise of the output amplifier over here. So, we can analyze the overall output noise by taking superposition of the noise contributed by these two resistors. So, first of all, let us see what is going to happen with R1. So, R1 has its equivalent noise, I can represent it in form of a noise voltage V N1. Suppose we do not have any signal, we are just considering the contribution of the noise of these resistors and trying to see how does it translate to the final output. So, first I will consider the effect of V N1, and we can see that V N1 is nothing else but it is behaving like an input signal, which will ultimately get multiplied by the gain factor R2 upon R1, because this is an AC ground or the DC potential, this will also be AC ground. Therefore, you have V N1 upon R1 signal coming in, and that current goes into R2, and therefore, you have this 0 plus 0 minus V N1 upon R1 times R2 voltage coming over here. So, V O N output noise, which is going to be minus R2 upon R1 times V N1. Therefore, it gets multiplied by the gain factor that you have chosen. If you are choosing a gain factor of say 50 or 100, we can see that the R1 noise will also get magnified. Whereas, if I look at R2, if I am looking at the overall noise contribution, setting V N1 0 and just considering V N2 appears as it is. So, if I consider this to be 0 and then look at only V N2, that does not get amplified by this circuit. So, that remains as it is, and therefore, the noise contribution by this feedback resistor will not be amplified as compared to the signal. The signal is getting amplified by the factor R2 by R1, but the noise contributed by the feedback resistor, that is the resistor R2, that is not getting amplified. So, this amplifier will amplify the input signal and V N1 by the amplifier gain, but not the noise contributed by R2. Therefore, the signal to noise ratio will not be distorted significantly by the noise contributed by R2. Also, if we look at the feedback configuration, we can visualize what is the role of R2. So, as we said, this particular feedback is acting like a shunt feedback. You have an output signal which is voltage VO, which is being sensed by this feedback element R2, and it is producing an effective signal. Right now, I am not saying whether it is a current signal or a voltage signal, it is producing an effective signal which is going into the input node, and it is getting mixed with the same node where the input signal is coming. So, whenever there is a combination of feedback signal and the input signal at the same terminal, there is a shunt connection, and we know that it is going to be a current mixing, because current mixing happens at the same node. If you have to subtract voltage, then it happens at different node. So, if the feedback signal is coming at the complementary node as compared to the applied input signal, then it is a series feedback. The input quantity is subtracting from the feedback quantity, because the feedback terminal or the feedback signal is fed to the complementary terminal. But here we see that the feedback signal is fed to the same terminal as the input signal, therefore, the input quantity has to be treated as current. And as a result, if I look at the role of R2, it is basically providing a current feedback at the input point. In order to treat or analyze this feedback amplifier, we need to analyze this as a shunt amplifier and need to analyze a given input source also as a current source. So, even though we are using this amplifier topology as a voltage to voltage amplifier, but the mechanism is of a shunt amplifier. And therefore, if I look at an applied input source over here V in, we would like to first convert it into its equivalent Thevenin current source. So, let us assume that you are having a input signal V in. So, I can represent that as an equivalent current source V in upon R 1, and its equivalent source resistance becomes R 1, right. If you are having V in series with R 1, we can convert it to its equivalent Thevenin equivalent current source and the corresponding source resistance R 1. Then it goes into the input of our amplifier, and the R 2 is basically now can be seen as mixing current, sensing voltage and mixing current. Therefore, you are having voltage sensing and current mixing at the input port, shunt at the output, shunt at the input. And once again, if you look at the polarity, if the input current is increasing, that means the voltage at the negative terminal is going to increase in the amplifier's input. As a result, the output voltage over here is going to reduce, because if this is the input is the negative terminal. If this increases because of an increase in the input signal current, the voltage over here is going to reduce. As a result, the current flowing from this input point to the output is also going to increase, that is the I feedback flowing through R 2 is also going to increase. So, if the input current is assumed to be increasing, we see that the IF also increases. Increasing input current increases the voltage over here, whatever is the overall input impedance, this input current increasing will result in increasing input voltage, that will result in reduction in the output voltage, because this is a negative terminal. 0 minus this voltage increasing will lead to reduction in the output voltage, and as a result we will have the increase in IF, that is the feedback current flowing from the negative terminal of the amplifier to the output. As a result, we say that the feedback current is increasing as the input current is increasing, therefore, it is subtracting from the input current. In effect, if it is an op amp based on CMOS circuit, we can assume that the input current going into the negative terminal is almost 0, and therefore, the I in is almost similar to IF, whatever is the input current provided by this source into the main amplifier. If I assume that this resistance can be clubbed with the source, whatever is the input current provided by this particular source entirely goes into IF. That is the current feedback operation we can visualize. As a result, if I need to look at the overall contribution of R 2, I need to look at its equivalent current contributed as a noise. So, we know that if I have to look at the noise voltage of R 2, it is 4 kTr. However, if we look at the equivalent current, I can represent the equivalent current noise of a resistor once again by taking the Thevenin equivalent and writing it as 4 kT upon R, and as a result the noise current contributed by R 2 also reduces as the value of R 2 is increased. So, if you have a very large R 2 in the feedback, the noise current contributed by R 2 in the feedback will be reduced as compared to the feedback current, and as a result we can say that a larger value of R 2 effectively is going to diminish the contribution of noise current contributed by the feedback element to the input point. Therefore, the current mixing will not be influenced so much by the noise current contributed by R 2. So, looking at this feedback topology, we can assume that the R 2, if you are making it large, even then because of this current mixing topology, it is not going to corrupt the input signal over here. It is not going to significantly corrupt the feedback current coming through the resistive path. As a result, what we can conclude from here is that because of the current mixing topology, current feedback terminal over here, a large choice of R2 does not corrupt the feedback signal coming from the actual capacitive feedback, and therefore, it is not going to significantly corrupt my output signal on the overall closed loop feedback operation. So, now let us see what is the role of this R2 in frequency response. So, we have just looked at the overall noise response. We also need to take care that it is not interfering with the specification of frequency response that we have started with. So, we have looked into the high level specification, and depending upon the signal, we estimated that our signal content is going to be in the range 0.5 hertz all the way to around 100 hertz, and putting this R in parallel with C in the feedback path should not interfere with this. We should still be able to satisfy this condition. So, let us see whether that is getting sacrificed. If yes, then what is the value of R2 needed in order to meet this criteria.
Voltage across R1 is 0, so can we remove the R1?
No, ultimately this current, this is inherently a voltage to voltage amplifier. This op amp is a voltage to voltage amplifier. So, in order to amplify signal, you need a voltage over here. So, this current ultimately produces a voltage that produces a amplified voltage over here. But overall, this configuration is a shunt. So, this op amp along with the resistive feedback is producing or is implementing a current to voltage amplifier. So, we have seen in the feedback discussion that the op amp can be used to build any of the 4 topologies of feedback. It can be shunt, series, shunt. So, it can be used to implement current to voltage amplifier also, although inherently this triangle, that is the op amp, is basically taking a voltage at the input and producing a voltage at the output. So, if you model an op amp, it is modeled as R in at the input point, and you are having some output resistance R out, and you are having A times the VE, where VE is the voltage across its input terminal. So, this will be the model for an op amp, because ultimately it is amplifying the voltage appearing across the 2 input terminal. It has some effective output resistance. So, this is how I would model an op amp, but I can implement any one of the 4 topologies of the feedback using op amp, and in that case the overall amplifier has to be modeled corresponding to the topology. So, here I can model this amplifier as a current to voltage amplifier. For that, we can characterize this amplifier. So, I can ask you to find out the overall 2-port network model of this amplifier as a current to voltage amplifier. You should be able to do that. You should be able to find out the equivalent input resistance, the current to voltage gain, and output resistance if I have to characterize this as a current to voltage amplifier. So, although I am using this op amp to build my circuit, but effectively topology wise this is a current to voltage amplifier. Any other question before we proceed towards the frequency response? So, for the frequency response, once again I have to go back and add my original feedback components that are my capacitors. So, let us do that. Once again I am using only the single ended version just to keep the analysis simpler. Call it C2. So, this is the overall circuit, and here we know that overall response will be given by Z2 upon Z1. So, I can just write it down as Z2 upon Z1 minus sign, which is where Z2 is parallel combination of RF and C2. So, I can find out Z2 first, which is 1 upon SC2 parallel RF upon RF plus 1 upon SC2, and this is going to result in RF upon 1 plus RF SC2, and therefore, the gain is the closed loop gain is minus Z2 upon Z1. So, RF Z1 is 1 upon SC1. So, you have SC1 upon 1 plus RF SC2. So, what kind of transfer function do we see here because of the RF? If I want to plot this as a function of frequency, what is the transfer function do I get? At very high frequencies, the RF SC2 term is going to be much larger than 1. As a result, I can ignore this 1 with respect to this RF SC2, and therefore, what is the transfer function? It is going to be my required, the desired gain C1 upon C2 minus sign mod, if I am just taking the mod of that. So, this is your mod A. So, at high frequency I get C1 upon C2. However, if I go towards lower and lower frequencies where S or where RF SC2 is becoming much smaller than 1, or S is becoming much smaller than RF C2, 1 upon RF C2, the RF SC2 term will be ignored with respect to 1 in that case, and for that scenario AF will just become minus RF SC1. That means, if I look at the modulus or the magnitude of the gain, it will be dropping towards lower frequency. As I go towards lower and lower omega, the gain will also become lower and lower. So, what is the frequency beyond which it is happening? This is the 1 upon RF C2. Beyond that, you are having the drop because of the high pass operation, because of the pole coming over here. So, we are having an overall high pass transfer function resulting from this RF and C2 combination, and we have just figured out that in order to allow our neural signal to pass through this amplifier, we must make sure that this cutoff frequency is higher than 0.5 hertz. So, I must make sure that or lower than greater than or equal to 1 upon RF C2, that must be smaller than or equal to our minimum signal frequency, which we have said 2 pi times 0.5 hertz, and that would imply that RF must be greater than 1 upon 2 pi 0.5 times C2. Now, let us see what is the possible value of C2 that we get from here. So, we have seen that the C1 C2 values, how are they going to be determined and how are they going to be constrained. So, in order to get larger gain, we would like to have C1 larger and C2 small, and suppose we target a gain of say 50 to 100 from a single stage. In that case, C2 is 100 times smaller than C1, and a ballpark number, the maximum value of a capacitor that you will have in a single channel, suppose it is 10 picofarad, is also on a higher side. Generally, it can be further smaller, but suppose we are choosing C1 to be 10 picofarad, and as a result C2 is around 0.1 picofarad, just rough numbers. So, in that case C2 is 100 femtofarad, and once again we have to make sure that this C2, the smallest value of C2 that we choose, is sufficiently higher than the parasitic capacitance of the MOSFETs in the operation amplifier, otherwise you will not get a precise gain. So, that will be the lower limit on C2, if you want to just recall that. Now, in that case I have to make sure that RF is greater than or equal to 2 pi 0.5 times 10 to the power of minus 11. So, basically a huge number. So, this is something close to or higher than 10 to the power of 10, and this was 10 giga ohm range. Therefore, RF must be greater than 10 giga ohm. So, this is a huge number, and therefore, we have to see whether it is at all practical to implement such a huge number using passive resistance. The answer would be no, definitely, because passive resistance at the max they can achieve values of around say mega ohm, few mega ohm is feasible, but beyond that achieving such large values of RF will be very difficult, and this value is definitely impossible using passive resistance. So, rather than using passive resistance, people have explored other techniques through which using transistors we can implement such large values of RF. So, we will look at techniques where transistors operating in subthreshold regime very close to the off condition can be used to implement such values of RF. So, rather than relying on passive resistors, we will be looking at how to implement such large resistor values, effectively large resistor values using transistors. So let us look at one particular example and try to see how such a high impedance value can be obtained from a combination of transistors. Any question before we proceed? So here we have just looked at the frequency limitation and trying to make sure that the RF value that we are choosing is in line with our frequency specification, bandwidth specification of the amplifier, and then we arrived at this huge value, and then we have to look at the circuit implementation. How do we really go ahead and implement this using transistors? And another point that we noted was, if you have large RF value, if you look at the equivalent feedback contributed by RF, that will be small. So we are looking at the equivalent noise contribution or noise current contribution. So if you are implementing it using large, if you are using such a sub-threshold regime transistors to implement such an RF, the overall noise current will also be small because of the 1 upon R dependence of the noise current. So now let us look at the transistor level implementation of RF and try to see what are the non-idealities that we may need to address. Any question before we proceed towards transistor level implementation? Okay. So one of the implementations used in literature is a series combination of two MOSFETs. I am using P MOSFETs, where you can wherever I am drawing the dots, they are having connectivity. Where there are no dots means no connectivity. They are just crossing points. So the input signal is over here. This is the input terminal of the amplifier. So basically, you can say the negative terminal of the amplifier or the positive terminal of the amplifier, and this is the input signal. The input point is connected to the gate of this particular PMOS. The input terminal of the amplifier is connected to the second PMOS. Here you don't have any connection. Now, if you look at our negative feedback configuration, if we are having such a resistor realized between these 2 points, and of course we have this capacitor feedback. So basically we are building this large resistor using this series connected transistors, and we also need to check what is the voltage conditions across these 2 terminals that we are going to have. Now, at the input point we have some AC signal coming, and it is capacitive coupling. So we do have some minute input signal coming at this point, and this point we have just established. We are trying to establish a DC bias with the help of this large resistors. So assume that you have a good DC bias established. We know that the input of the gates of the MOSFET devices, which are forming the input terminal, they don't sink in any current. So there will be zero current going into the input terminal. So under DC condition, we can assume that whatever is the output DC potential, the same DC potential will be available over here, right? Because ultimately you have the negative and the positive terminal of the amplifier going into the gate of the MOSFETs of the differential amplifier, as we have seen, and they don't sink any current. So if you talk about absolute DC values, whatever is the DC value present at the output will be same as the DC value present over here. So despite having very large resistor, DC point of view, even if there is a very small minute nanoamperes, picoamperes of current flowing through this, in long term, in few seconds at least, it will make sure that the DC potential at these 2 points are coming to be same. And that is the basic mechanism through which, despite using such a large resistor, we get almost the required DC point over here, same as the DC point which is available at the output. For the fully differential case, we know that we have established an appropriate DC point at the differential output. So in our fully differential amplifier, we have differential output, both of them are set to a required DC point, where is the common mode DC voltage, and with the help of this resistor, large resistor connected between the 2 outputs and the inputs, we are ensuring that we are able to establish the same DC point at the input as well. So you are having minus plus, and both sides you are connecting the inputs with the corresponding outputs. and of course, along with that you have the capacitor as well. So, on both the sides we are ensuring that the input DC points are equal to the output DC point, which is set to the common mode voltage. So, the output terminal, the right terminal of this series connected transistor is connected to the output point of the amplifier, which is going to have amplified signal level as compared to the input signal, and here we have the left end of the transistors connected over the negative and the positive terminal, which are acting as AC ground. You do not have much of a signal over here. So, as a result, what we can say is you are going to have sufficiently larger signal at this point, whereas the other end is going to be relatively stable, it is not going to have much fluctuation over here. So, we have to see what happens when the signal at the other end is going up and down with respect to the DC potential. Remember, DC point to be, what we are assuming is that the DC potential at these 2 points and the input points are same. Therefore, the DC level at the output point is also similar to the DC level at the input point. So, the DC levels are same, because this resistive feedback has ensured that the DC point here and here is remaining same, whereas the signal is much higher. You have an amplified signal at the output point. As a result, with respect to the left terminal, the right terminal is going to have a sufficiently large signal swing. So, as this signal changes, we can see how the effective resistance of this series connected transistor pair changes. So, let us look at the, say, positive cycle. When the signal is going high, what is the condition of each of these transistors? They call them M1 and M2. So, when the signal is going positive, we can see that the gate potential of M1 is increasing, whereas the gate potential of M2 is relatively constant. We know that MOSFET is a bidirectional device. So, the definition of source and drain depends upon the relative potential across the two terminals. So, for a PMOS transistor, whichever terminal is having higher potential, higher absolute potential, that is the source. So, for both these MOSFETs, because this is for the positive cycle, this is the higher potential, this is the lower potential. As a result, the midpoint is also expected to be definitely higher potential than the V in. So, when the signal is going up, this point as well as this point is higher than the V in. Now, if I look at the condition of M2, for M2, therefore, since this is at the higher potential, so this is the source terminal for M2, and the gate of M2 is V in, and therefore, the VSG is becoming positive. So, for the positive cycle, the VSG of M2 is positive, whereas if I look at the condition of M1, for M1 also, this is your source terminal, because ultimately this is a higher potential, this is a lower potential, midpoint of that, it may not be exactly the midway, but it is supposed to be higher potential than this one. So, this is going to be the higher potential and the source terminal. This is definitely lower than the potential over here, whereas the gate potential is higher. So, although the source potential is higher than the drain potential, but the gate potential is even higher than the source potential, and therefore, the VSG of M2 is becoming more and more negative. So, VSG of M1 is becoming negative, and therefore, the resistance of M1 will be, you can say R of M1 will be going up very strongly, whereas R of M2 is going down. This is a series combination. So, ultimately, the overall resistance, that is RM1 plus RM2, if the RM1 is strongly going up and becoming relative is remaining relatively off, because VSG is becoming more and more negative. Therefore, this is going to dominate the overall resistance between the two terminals, and therefore, the effective resistance between the two terminals V in and the output point is going to be very high, determined by the off resistance of M1. This is clear. So, this is trying to keep this overall resistance very high despite the signal going up. What happens to the negative cycle? So, negative cycle also we are going to just have the reverse condition by symmetry. So, you can see when the signal goes down a little bit, now for both the MOSFETs, this is at a higher terminal, higher potential. As a result, for M1 this becomes the source, for M2 this is going to be higher potential than the other one, because this is higher than the other extreme for the negative cycle. So, for the negative cycle, this is the source of M1, this is the source of M2. So, this midpoint is source of M2, the V in becomes the source of M1. Under that condition, what we see is for M1, the VSG M1 is becoming slightly positive, because V in is higher than the V out over here. So, this is basically your V out. So, V in is higher than the V out under the negative cycle. As a result, the gate potential of M1 is getting lower than the source potential. Therefore, it will try to get on. It may not necessarily get on, because I am not saying that the gate potential is lower or the VSG is greater than mod Vt of the PMOS, but still the VSG is positive. So, although it will be still in subthreshold region, it is not completely on, but definitely its resistance will be reducing as the signal is going down. So, as the signal goes down and down as compared to the DC line, the gate potential of M1 is reducing with respect to the input potential, and therefore, the VSG is reducing, therefore, the impedance of M1 is reducing. If I assume that this is in subthreshold regime, the resistance of M1 will be reducing exponentially, because we know that in subthreshold regime the resistance of the transistor, current for the transistor is exponentially dependent upon VSG. Therefore, as the VSG is becoming more and more positive, the impedance of M1 will be reducing exponentially. Now, if you look at M2 on the other hand, once again we have the reverse condition. The gate of M2 is V in, which is at a higher potential as compared to the source, because this is a source of M2 which is going to be definitely lower than the V in, because of voltage division you are definitely getting this point which is lower than V in, and as the input signal or the output signal is becoming more and more negative, we are going to have the overall potential over here becoming all the more lower, because this is getting on. Therefore, this will try to connect these 2 points more closely. As a result, this potential will follow more closely V in. Therefore, this becomes closer to V in, because if you look at the simple voltage division, because this resistance is much smaller now as compared to this, therefore, this point will be closer to V in. As a result, this potential is also getting, as compared to the gate potential, you are having 0 or negative VSG for M2, and therefore, once again the VSG of M2 in this case is negative, and therefore, the R M2 will be increasing exponentially, R M1 is reducing exponentially. So, what we can see is that in the negative cycle, once again the reverse phenomena is true, resistance of M2 becomes much higher and M1 becomes much lower. The series combination is going to be determined by the much larger one, and therefore, the overall impedance over across the V in and V out stays high for the positive as well as negative cycle. And for the subthreshold operation, since the impedances are going to be much smaller, we are having a negative VSG for one of the MOSFET, we can ensure much higher impedance provided by these MOSFETs. So, even when the VSG is off, the device will have some minimum leakage flowing through the drain and source. So, there is always a non-zero leakage current between the drain and the source. That is what is going to give us a very large impedance value, a very large resistance value. And throughout the cycle, whether the signal is going positive or negative, we are ensuring that the impedance provided by the overall series combination is corresponding to the off state impedance of the transistor, and hence it is staying very high. So, by appropriately choosing the channel length, for example, we can also try to push the impedance higher, and it has been shown that this kind of combination can be can help us in achieving resistance all the way up to 10 to the power of 14, 10 to the power of 15. Here our target is 10 to the power of 12. So, definitely that is also achievable using appropriate device dimensions. The problem in this particular case, if we are operating in subthreshold regime, we are not sure how precise these resistance values will be. So, here we are relying on the assumption that this feedback component will be able to meet our bandwidth requirement. RF we are trying to choose is such that it is not suppressing our desired signal content. If we are relying on subthreshold operation of the transistors to realize such large value of RF, it is going to be highly sensitive to temperature and process variation. Subthreshold region, because of exponential dependence of transistor currents on threshold voltage variation or temperature variation, it can have very sharp or very strong dependence on temperature and process, and as a result it will not be very well defined, very well controlled. In simulation you will be getting some value, but the actual implementation can give you drastically different value, and therefore we may end up blocking our desired signal component as well, because this RFC2 can end up lying much lower than the expected value, or it can happen the reverse way, it can end up lying much higher than the expected value. So that is not a very well controlled value, it can vary a factor of tens or even higher. So it will be good to have some kind of tuning option or calibration, so that this large value of resistor is calibrated or tuned as per requirement. So we need to have some post silicon calibration or tuning option, so that it is controllable or adjustable. In the silicon we are having the option of tuning and matching it to the required value, because in simulation you may be expecting some values, but in the silicon you can end up having very different value because of a small change in the VT, or over the time also the resistance can change exponentially because of the subthreshold operation, and hence you can end up having very different R value and hence a very different frequency spectrum on the lower side of for our amplifier, which is not desirable. Therefore, we will see that how to incorporate some tuning option in this circuit. Let me go back to the differential amplifier. If I am connecting, my output DC point is fixed with the help of the common mode feedback. So that is fixed, and the input is just having some connection with the external electrode with the help of a capacitor. So there is no DC path through the capacitor, there is no DC path through the transistor, and therefore if you connect some very large resistor between the output to the this point, the transistor is not a perfect insulator, you are having some leakage current through that. Even if it is off, it is providing a very large resistance, and as a result it will ensure that whatever DC point is obtained over here, the same almost same DC point is obtained over here, because there is in the steady state there is no current flowing into the gate of the MOSFET, there is no DC current flowing into this capacitor. So if the total current flowing here is 0 in steady state, that must make sure that this DC potential is same as the DC potential here. This is clear?
Say in AC it will block.
AC because
Output voltage can go in input port also.
no, so for the DC response, once again, because we are having very large R value, and at the input side you are having an impedance which is much smaller than the R. So if you take superposition, because of the output signal, there will be hardly any impact on the input side. Even if I just assume that you are applying some output signal over here, what is its impact on the input? So we can see that you are having some input impedance over here, which is just around mega ohm. So we have seen that the electrode impedance there is approximately around mega ohm. So here you are having around 10 to the power of 10 or 10 to the power of 11, and here you are having mega. So it's 1 mega. So still it is much larger. Therefore, if I assume that okay, let us apply some output signal over here, and what is its effect on the input? That is not going to be so much. It's very minute.
So you told that the resistance can change over time. So if this condition satisfied that the cutoff frequency is proper, then if it is increased the resistance, can it be problematic? If it is decreased, then it is have some issue. But if it is increased,
then it has issue, because it is going towards lower frequency also, and then you can have more artifacts coming into picture. So we also want to suppress low frequency artifacts. So we have discussed the issues of dynamic offset. So if you are lowering the cutoff frequency, it will pass those low frequency artifacts also. So we don't want to invite the low frequency artifact sitting as 0.1 hertz or something. So we want to block them. So lower side also it can create problem.
Sir, but it is a first order filter, so
First order filter is not enough, definitely. So as we have discussed, we want to incorporate filtering operation in the main amplifier itself using some additional feedback operation. So that also will be seeing that. I guess in some of the simulation exercises also we have seen how to incorporate a feedback loop which can take care of that additional low frequency component. So it can incorporate some filtering operation in the main front-end amplifier itself and give you a higher order filtering effectively. This is the concept of servo loop as we have discussed. So similar thing will be coming.
Behavior of noise in the MOSFET will be same as the resistor.
No, MOSFET noise is dependent upon the overall, the thermal noise of the MOSFET and 1 upon F noise of the MOSFET. You have to model it according to the MOSFET parameters. So, for example, thermal noise of the MOSFET, if you look at it, so you are anyway having very small GM, 4 kT gamma GM will be the thermal noise current of the MOSFET. So, if you are using subthreshold regime MOSFET, GM is anyway going to be very small. The overall current flowing to the MOSFET is anyway very small. So, the thermal current, which is proportional to 4 kT gamma GM, will also be very small. Therefore, it will not interfere with the feedback current provided by the capacitors too much.